Today, great pleasure to introduce Bruno Martelli from Pisa, who's going to talk about fibering and monodromy. Bruno.
Okay, thanks. Thank you, Alan. Thanks. I would like to thank the organizers for inviting me. It's a pleasure to be here. Since I am the last speaker today, I think I have a good excuse to avoid all technicalities. And since we don't want to miss the bus, I will probably finish before the end of the hour. So I will start by quoting a theorem of Thurston. It's always a good idea to start a talk by a theorem of Thurston. Okay, so this is a major theorem in three-dimensional topology, which says that if you have a three-manifold compact that fibers over the circle, okay, then the manifold is hyperbolic if and only if the monodromy is pseudo-Anosov. Okay, I will explain some of the terminology. So this is one of the most important theorems in dimension 3. It's part of geometrization. Okay, so geometrization of three manifolds can be stated in two ways. Either you state every three manifold decomposes into some pieces, and every piece belongs to one of 8 geometries. Or you concentrate on the hyperbolic geometry, which is the most interesting one, and you say if a manifold satisfies some requirement, then it is hyperbolic. And that's the case. This is the version of this second kind of statement, which concerns only three manifolds that fibers over the circle. So geometrization of three manifolds that fibers over the circle looks like this. And I will explain some of the terminology. So hyperbolic means that the interior of M has a finite volume complete hyperbolic metric. So for me, hyperbolic will always mean complete and finite volume. And actually, it's not M, it's the interior of M who has such a metric. But I will, as usual, confuse every compact manifold with its interior. Okay, so whenever I talk about a hyperbolic structure on a compact manifold, I always mean in the interior. Okay, so what do I mean by the monodromy? So every time you have a manifold that fibers over the circle, it looks like this. So you have a circle on the base, and then every fiber is a manifold. And then you can carry this fiber along the fibration, and then when you come back, you get a map from the fiber to itself. And the map phi is a diffeomorphism. And of course, there is not a unique way to do this. There is no canonical way there is no flat connection of any kind. So there is no canonical way just to drag the fiber along the circle. So phi is not uniquely defined. So phi is only uniquely defined up to isotopy. So phi is the monodromy, and it is uniquely defined up to isotopy. Up to isotopy means that I am allowed to compose phi with an isotopy of the surface. Okay, so yeah. And pseudo-Anosov is the more complicated term in this statement. Usually you say something like this. You say that there is a representative. So phi is uniquely determined up to isotopy, but you can choose some representative which is better than others. And in this case, there exists a representative. So pseudo-Anosov means that there is a representative phi which is well behaved. And you can say, for instance, that fixes two transverse projective measured laminations or you can use the word foliations. Actually, it should be singular foliations, but we just say foliations. And of course, defining these objects needs some care. I don't have the time to do it now, but I will say something more later on. What is important here is that this representative is actually unique. So there is a unique, nice representative for phi. Unique, of course, up to conjugation. You cannot expect phi to be just unique. It's unique up to conjugation, okay? So in particular, phi has an interesting dynamics, which is not defined here. Here there is no dynamic because phi is only defined up to isotropy. Now that you have a preferred representative, now phi is really unique and, okay? Unique up to conjugation, okay? Is that clear? Okay. So this is one theorem in dimension 3, and there is also another theorem proved by Jan Egel. Okay, so the theorem says that there are many three manifolds that belong to this class. Okay, this theorem says that every hyperbolic three manifold virtually fibers. So it means that if you have a hyperbolic three manifold, and this always means complete and finite volume, maybe the manifold does not fiber over the circle because, for instance, the first Betti number could be 0 or some other reason. But nevertheless, it will have a finite index subgroup. There's going to be a finite cover which fibers over the circle. Okay? So this theory in particular says that there are plenty of examples. Okay? Okay, now the question that I would like to arise today is whether we can hope for this theorem to be valid also in a higher dimension. Okay, so this is the question I raise today. So can we state a reasonable theorem of this kind in higher dimension, and could it be true? Okay. So the first thing is, can we state something reasonable? Okay, so here, okay, so here it is obvious to extend this theorem to a question. Okay, so the question is, does every hyperbolic and manifold virtually fiber? Okay, this is a reasonable question. The only case where it is obviously no, the answer is when n is even. An even-dimensional manifold, an even-dimensional hyperbolic manifold does not fiber because the only characteristic is always different from 0. Okay, so I should add the hypothesis n odd. Okay. But this is the only requirement I know. So for the moment, I know no counterexamples to this question. It's a very bold question, of course. There could be some counterexamples, but I'm not aware of any. The only thing I know is that there is at least one example. Okay, so the example that we constructed with Giovanni and Matteo. So it's a very specific example. So there is a particular, so the first dimension to look at is of course, it's dimension 5, since in dimension 4 there can't be any example. So in dimension 5 there is so there are only few papers about hyperbolic 5 manifolds, but some of them were in literature already 20 years ago. In particular, there is a candidate, smallest hyperbolic 5 manifold, which is discovered by Ratcliffe and Chance. Yeah? No, it's a surname. It's somewhere here in the audience. It's over there. Yeah. I'm not that patriotic. Italians are not very patriotic in general, except for football, but not about the mathematics. Okay, so there exists an example, and the example has a name. So the Ratcliffe, Chance, hyperbolic 5-manifold, fibers over the circle. Okay. Okay, so since there is at least one example, it makes sense to ask whether this question has a positive answer or not. Okay, once you have one example, actually you have infinitely many, because examples they propagate in two directions. So, for instance, whenever you have a hyperbolic manifold that fibers, then every finite cover fibers. And moreover, if the manifold has a large first Betti number, something which can be usually achieved by taking a finite cover, then here, if the first Betti number is, I don't know, 27, then in fact you can find infinitely many fibrations just by perturbing the class in the first cohomology group. Okay, so if you have one example, then you get infinitely many examples, but they are somehow all related. All the examples we know arise from this single one. Okay. So I know nothing about this question. Actually, today I would like to talk about the first theorem. And in fact, I've been working only on this in the last 2 years, more or less. So I would like to understand what is going on here. So is it possible to have a theorem like this one in a higher dimension? So this is even bolder than the other one. So the point is that let us look at dimension 5. So we have a compact 5-dimensional manifold, hyperbolic manifold, and we would like to have a theorem like the manifold fibers if and only if the monodromy fulfills some requirement. Okay, now here is complicated because it's not so easy to find a higher dimensional analog of this condition. Okay, so the only thing we could do, and that's what I did, is to analyze the only example I know. Okay, so I've spent a lot of time to analyze the only example I know to understand the fiber and the monodromy, to see if there is something going on which looks like this. And the answer, I think, is positive. Okay, so I think that in our example, somehow the monodromy is pseudo-Anosov in some sense. Okay, so the talk today is, I want to convince you that there is that this notion makes sense also in higher dimension, and maybe this is what happens, at least in the examples that we know. Okay, so I will start by giving some information on the general problem here. So suppose in general that, so we stick to dimension 5, although this is general, but let's stick to dimension 5. So suppose that you have a theorem. So pick a 4-manifold. Every manifold will be compact, possibly with boundary. Okay, pick a 4-manifold, and the self-diffeomorphism phi. Okay, now of course, so every time you have a fibration, you have a monodromy, but it goes also the other way around. So every time you have a diffeomorphism, then you have a fibration. Because it's simply constructed by taking the 4-manifold M times an interval. Okay, so you have M times 0, 1. And then you glue the right part to the left part using phi. And then you get a fibration over the circle. Okay, because these 2 points are identified. Okay, so having a fibration and having a monodromy is more or less the same thing, except for the fact that the monodromy is well defined only up to isotopy. So suppose you have a 4-manifold and a candidate monodromy, then you have a 5-manifold that fibers over the circle, and then you ask, is it hyperbolic? So most likely no, but there are some obvious requirements. So if M phi denotes the 5-manifold you get. Okay, so M phi is the 5-manifold you get, which fibers over the circle with fiber M and with monodromy phi. Okay, if this is hyperbolic, so then there are some obvious necessary conditions. Okay, so the first condition is that the fiber M should be aspherical. this is because hyperbolic implies a spherical, and if you have a manifold that fibers over the circle, which is a spherical, then the fiber is a spherical. This is just an obvious consequence of the sequence in homotopy for fibrations. Moreover, there are some other consequences. One is that every properly immersed annulus or torus, which is essential, so it's every properly immersed and essential annulus or torus is parallel to the boundary, so can be homotoped relative to the boundary. Okay, so properly immersed, we know what it means. Essential means for it that it is pi1 injective and not boundary parallel. So, yeah, in fact, the way I stated is essential means pi1 injective. Okay. Okay. If you add the okay. Okay. So there are no. Yeah, no, I'll state it the other way. So M is a spherical. Every properly immersed essential and essential means pi1 injective plus not homotopic to the boundary. Okay, so there are no essential annuli and no essential tori. This condition can also be made in a very simple way. It's an algebraic condition on the fundamental group. So it means that every z times z is peripheral, and the loops on different boundary components are not freely homotopic. So this is just a condition on the fundamental group. And another obvious condition is that, so since this is a fiber on a fibering 5 manifold, if there are some cusps, then the fibering 5 manifolds, the boundary of a hyperbolic 5 manifold is a closed flat 4-dimensional torus, and the fibration restricts to this closed 4-dimensional, I say torus. No, it's just a flat closed 4 manifold, and the fibration restricts to this flat closed 4 manifold, and the fiber must be a closed flat 3 manifold. Okay, so the other condition is that the boundary of M consists of flat closed 3 manifolds. Flat means that they admit some flat structure. It's not important which one. And moreover, each boundary component is pi1 injective. This is also a consequence. So of flat, pi1 injective. Okay. So these two conditions are already very strong. In fact, if you state the same conditions in dimension 3, they imply that the manifold is hyperbolic. Because this is like saying that the boundary is incompressible, this is an annular, a toroidal, a spherical. So in dimension 3, these two conditions imply that the manifold is hyperbolic by geometrization. I can say maybe here that it's not really hyperbolic, it's hyperbolic. Okay, so in the 90s, when geometrization was not yet proved, we said that a manifold was hyperbolic if it fulfilled all the homotopy conditions to be hyperbolic. Okay? In this case, in fact, this is certainly not hyperbolic because there is a third consequence which will prevent the manifold to be hyperbolic. So the third condition is that the monodromy must be quite complicated enough. Okay, so phi star acts on so phi stars acts on the conjugacy classes of the fundamental group of M. That is on closed loops up to free homotopy. So it acts on conjugacy classes of pi1M, and it mixes all of them in the sense that if you exclude the peripheral classes that can be fixed, all the other classes are never fixed, though the orbits are infinite. So the non-peripheral class, so the non-peripheral classes form infinite orbits. So except for the boundary, which is just a union of flat three manifolds, so all the other closed curves in the interior, they're never fixed, not even by some power of phi. The reason is that if there was some closed loop here in the manifold, like here, which is fixed by phi, then this will give you an essential torus. Okay. So, yeah, and even if it has a finite orbit, then you get an essential torus. So this is the usual argument you use in dimension 3, but it works in all dimensions. Okay. So in particular, this implies that that phi star has infinite order in the outer automorphism group. Okay, and this prevents the manifold from being hyperbolic because by most of rigidity, this group is finite. Okay, so what I wrote here maybe is a bit misleading, but the point is that the first 2 points, it's really something you feel. So the fiber looks like a hyperbolic for manifold, but it's not because of that. Okay, is there any question about this?
What does flat mean?
Flat means it has a Euclidean metric. It has a metric with zero sectional curvature.
So in particular, by Weber theorem, it's just like universal cover is a finite quotient.
Yes. So there are 6 oriented flat closed three manifolds and 4 non-orientable ones, and of course they are all finitely covered by the three torus. Okay. Is there another question? Okay. So these are the necessary conditions for the fiber. Okay, and these are valid in general. So in particular for the fiber of our examples, these conditions are certainly true. And the point is that it seems to me that the fiber we have here is the first example of a manifold that fulfills all these criteria. So it's not so easy to build an aspherical manifold, which is atoroidal. So the fundamental group has no z times z, but it has an infinite order automorphism. Okay, this is the only example I know, more or less. In particular, I don't know any closed example. The only example of a manifold which fulfills these 3 conditions in any dimension greater than 2 is the fiber that we found. And I don't know any closed example. So let me just stress this point by asking a question. So is there a closed aspherical and manifold of dimension at least 3 such that the fundamental group does not contain z times z and the outer automorphism group is infinite. Okay, as far as I know, I don't know any example of this kind. Maybe there is one, but I don't know. Okay?
If it's closed, it's a priori that does not contain curves.
It's not hyperbolic. It's just spherical. Okay, so this refers to the fiber. So if there was a closed hyperbolic 5 manifolds that fiber over the circle, then the fiber will fulfill this. Okay, so there are no examples in dimension 3 because of geometrization, but in dimension 4 there could be some example of. Okay, of course a genus G surface is fine, but I'm asking whether there is some analog in higher dimension. Okay, is there any other question? Okay, so in particular, this shows, at least to me, that the monodromy of this fiber is something new, so which deserves to be investigated and to be understood. And so I spent a lot of time in understanding how the fiber looks like. So it's not easy because the existence of this fibration was done with some method, which is okay for finding fibration, but which was not really practical to understand the fiber and the monodromy. Okay, so it took me some time, but I think I understood what is going on. So let me first talk about the fiber. So this talk is only about one single example, which is the only example we have. So in particular, so let me, okay, so this is the theorem here. So there is a hyperbolic 5 manifold called the Radcliffe-Chance 5 manifold that fibers of the circle. Let F be its fiber. So F is a 4-dimensional smooth manifold. Everything I'm saying is I'm working in the smooth category. Okay. So I want to understand F, the fiber, and phi, the monodromy. This is the only thing I want to look at. And here's a theorem. So we give some topological information about the fiber. So the first thing is that the boundary of the fiber consists of 5 copies of a particular closed flat 3 manifold, which is the Hansch-Event 3 manifold. So there is a Hansch-Event closed 3 manifold. Okay, it's not important now to understand what manifold this is, but so in every dimension n there is a finite number of closed flat and manifolds considered only up to diffeomorphism. And in dimension 3 there are 6 orientable ones and 4 non-orientable ones. Among the 6 orientable ones, of course, the first one is the 3 torus. And there is only one of them which does not fiber over the circle, which is maybe the strangest of the 6. And this is called the Hansch-Event flat 3 manifold. Okay? It can be described as a branched cover over some link or some knot. But for the moment, it's not important. Of course, it is finitely covered by the 3 torus. Okay, something that looks like the 3 torus. And the fundamental group of F can be described by an explicit presentation, which is, so you have some generators. So the index goes from 1 to 6. The index I goes from 1 to 6. So there are 12 generators. And the relations are very simple. So AI plus 1 equals AI. No, AI plus 2 equals AI plus 1. Okay, this was optimistic. BI plus 2 equals BI plus 1. And those are some commutators. AI, BI equal AI plus 2, BI plus 2. Okay, so these are all indices are considered modulo 6. So there is a clear, obvious order 6 symmetry. And okay, so what is going on here? So this is the fundamental group. This is a Fibonacci group. This is the Fibonacci group of order 6. It's just the fundamental group of the Hansch-Event. Okay, and this is the fundamental group of another Hansch-Event. So the first two are just the presentation of 2 boundary components. Okay, and these are additional relations. So topologically, the manifold is obtained by taking 2 copies of the Hansch-Event. You attach a 1 handle between the 2, and then you attach 6 2 handles that give you these 6 relations. Okay, so you attach relations that of this kind. And then there are some 3 handles. So, okay, so you have a handle decomposition if you want. Okay. Now, there are many, so you already see 12 symmetries here. So this manifold is very symmetric. And, okay, the homology, the first homology group is finite. And the second homology group is very interesting because it's Z4. And okay, then the third one, Z4. And you can say that the only characteristic is 1. Okay, this is the smallest. Okay, only characteristic 1 is. Okay, this. So there is a conjecture that every aspherical 4 manifold has non-negative Euler characteristic. This conjecture is made for closed manifolds, but it can be extended to manifolds of these kinds. And okay, so this manifold fulfills the conjecture, but with the smallest non-zero possible number. This is quite interesting. This shows that the fiber is actually very small, and so it can be studied. And it is a four-manifold. So when you have a four-manifold, you ask some questions like, is it spin? What is the intersection form? Okay, so the manifold is spin. Spin implies that the intersection form is even. In particular, the intersection form, QF, can be computed. The second homology group is very interesting because it's Z4. And you compute the intersection form, and you get something like this. You get a matrix. Okay, so this matrix, so the matrix is invertible, but it's not unimodular because there is some torsion here. There is torsion on the manifold and in the boundary. This creates as a consequence, the determinant of this intersection form is not 1, it's 16. And the signature, you can easily see that it's 0. So this matrix has 2 positive eigenvalues and 2 negative eigenvalues. Okay. Okay, and you can also have handle the composition of the manifold or some picture. Okay. Now let's go to the monodromy. So let's look at the monodromy and see what it does. Okay, so the monodromy, you can calculate the action of the monodromy on all these topological invariants. So phi star acts on the fundamental group by sending. So the action on the fundamental group is well defined only up to conjugation because there is, of course, a fixed point issue here. Okay. However, up to conjugation, the action is explicit. I'm not going to write it, but every generator is sent to a word with at most 3 letters. So very reasonable. 3 letters, of course, in the generator AI and BI. What I liked is that the action on the homology is non-trivial. So phi star. So if you look at homology, of course, the action on the first homology group is not interesting because this is a finite group. It's not trivial, but it is, of course, of finite order, so it's not interesting. The action on the second homology group is much more interesting. And so it's like a matrix. It acts on Z4, like the following matrix, 0, 0, 1, 2, 0, 0, 1, 1, 1, 1, 0, 1, 2, 1, minus 1, 0. Okay, so when I computed this matrix, I said, oh, this looks like a Perron-Frobenius matrix. So maybe there is something like a 2-dimensional invariant lamination. This was, it's not, because there is a minus 1 here. And it's really not going to be a Perron-Frobenius matrix because the eigenvalues are plus minus 1 plus minus square root of 2. So there are 2 eigenvalues with the highest norm. And so this is not does not really looks like a Perron-Frobenius metric, but it's not. However, as a consequence, this is a matrix with, so 1 is not an eigenvalue. So in particular, no second homology class is fixed by phi. Okay, there's one thing I had to say before. So here, the second homology is generated by 4 elements, and these 4 elements can be represented by genus 2 surfaces. Okay, so you can represent the generators by 4 distinct genus 2 surfaces. Genus 2 surfaces. So, okay, so there are 4 genus 2 surfaces. These are their self-intersections. Okay. So in particular, what we get here is that the monodromy is going to move these genus 2 surfaces around, And there is no periodicity because the eigenvalues have norm different from 1. And so you're going to have infinitely many classes represented by genus 2 surfaces. This is not so common, okay? So in particular, we get the following corollary, is that so two things that are not so common arise. One is that, yeah, so in the second homology group has infinitely many classes with bounded Gromov norm. So they are represented by the same genus true, by surfaces of the same genus. Okay. Okay. Moreover, since these genus 2 surfaces form a basis, and since this is diagonalizable, so the eigenvectors form a basis, you also conclude very easily that the Gromov norm vanishes. So the simplicial norm on this homology group is 0. Okay, so this is so what is interesting here is that this manifold is atoroidal. This is the interesting point. So if you want to construct a manifold where there are infinitely many classes representing surfaces with bounded genus, or such that the Gromov norm vanishes on the second homology group, you're probably going to have a manifold with many tori, because the tori are the objects that you use to build self-diffeomorphism of infinite order. Anyway, so you usually have tori if you want to have something like this. So I think this is the first example of an aspherical manifold which has no tori. No tori means that all the tori are in the boundary and they are null homologous. So the no non-zero class in homology is represented by a torus. So there are no tori from a homological point of view. But nevertheless, the norm vanishes. There are no tori and no sphere, of course, because the manifold is aspherical. So no sphere, no tori, but the Gromov norm vanishes. And there are infinitely many classes like this. Okay? I don't think there is any other example of an aspherical manifold with these properties. The point is that there is this monodromy that mixes everything up. Okay? Is there any observation, any question? Okay.
So does it have any other diffeomorphisms? Is that the only element? So there's an arithmetic group that presents
Okay.
the quadratic form. Is that the only element in the group that?
Okay, so there are, okay, the fiber has many symmetries, and it has more symmetries than the one you infer from the hyperbolic 5 manifold which contains it. This is also surprising. This is like in the three-dimensional case. When you have a genus 2 fiber, of course the genus 2 fiber has many symmetries that are not induced by the 3 manifold that contains it. So, but I still don't know if the outer automorphisms group of the fundamental group is virtually cyclic or not. So I don't know if, in particular, I would like to know if it contains a free group of index 2. This would be nice. Maybe, I don't know. Okay, so I don't know how many elements are there in the, how many symmetries the fiber has. Okay. This I still don't know. Okay, so, okay, so another thing, okay, so now so what I would like to say is that in my opinion, there is something like an invariant singular foliation, but so I would like first to tell you what are the hints behind this fact. What are the hints? So there are some other facts. So theorem. So some other facts which I noticed at the beginning is that this fiber contains two surfaces, two phi invariant surfaces, two transverse phi invariant surfaces. Both surfaces are punctured tori. So. And of course, it makes sense to look at the restriction of phi to this punctured tori, and of course, it must be pseudo-Anosov. It must be. And of course, it is pseudo-Anosov. And the funny thing is that they have the same dilatation. So you have two surfaces like this, they intersect in 3 points. It's pseudo-Anosov on each, and they have the same dilatation. Okay. So the dilatation is this very simple number. And at the beginning, I was disappointed because this number does not look like the other one. Okay. But this, I think that this is just correct. Because the point is that you don't see invariant lamination by looking at homology, also for surfaces. If you are very lucky, for instance, if the invariant foliation is transversely oriented, then it comes out of a one form. And then you see it from the homology. You see so this number here is going to be the largest eigenvalue. Okay, this is not the case here. So the number we have here is smaller than the square of this. So this implies somehow that the homology doesn't see the invariant foliation if the invariant foliation is there. Okay, so what I'm saying is that I think that there is an invariant two-dimensional foliation, and there are two of them that are stretched with this factor here. But I'm going to say this very precisely now.
So the map is 2, 1, 1, 1 on both? Or?
Yes, it's on one torus. So one torus, the map is just you take the torus, right? You take the torus, and then you take this matrix, the simplest torus bundles over the circle. You take this matrix. The square of this matrix is this one. But this is already Anosov. And this matrix there is a point of so there is a fixed point, which is this one, and there's also a point of order 4, periodic point of order 4. So if you remove these 5 points, you get the pseudo-Anosov map on a torus with 5 punctures, and the 5 punctures go to the 5 boundary components of the manifold. Okay, this is what you get. So this is the eigenvalue of that matrix here. Okay, okay.
Why are you removing these points?
Sorry?
Why are you removing these points?
But I'm not removing them. It's just a way to describe what the fiber is. So there is a surface. So I'm describing one of these surfaces. One of these surfaces is a torus with 5 punctures. And I'm saying this torus with 5 punctures is realized in this way. Okay. Okay, I'm heading. So I'm telling what is true. Okay, what I think is true. The only problem is that I don't have a full proof, so I'm going to write this as a conjecture. Okay. So at the beginning, I didn't explain with all details what an invariant lamination or foliation is, because the point is that there are many ways to say the same thing, and only some of them have some reasonable extension to higher dimension. And the one that can be extended to higher dimension, and then that I think is true here, is the following. So just remind that, a very quick reminder. So whenever you have a self-diffeomorphism of a surface which is pseudo-Anosov, then what you get is that you look at Teichmüller space. You get a Teichmüller space. There is an axis. So phi preserves an axis. You take any point of its axis. There is no preferred point. You take one. This point will give you a Riemann structure on S. And this tangent vector is roughly something called a quadratic differential, which is a section on some bundle. But this quadratic differential here will give you not only some laminations, but also a singular Euclidean structure. And this is what I think extends to higher dimension. So what you get here is that, so this vector here, which is a quadratic differential, is some object, and which gives you a package of things. The most important thing here is that it gives you a singular Euclidean structure. On S, okay, where there are only finitely many singular points, and every singular point has a cone angle which is a multiple of pi. Okay, And there is also the subtlety here that k equal 1 is allowed only for punctures. So if the surface is closed, k is always at least 3. If there is some puncture, then on the puncture you can allow k equal to 1. Okay? And more than that, it also gives you a pair of two invariant foliations. Okay, so you get a singular Euclidean structure, and then it also gives on every tangent point a horizontal direction and a vertical direction. These directions will form true invariant singular foliation. But this is the object that I think extends to higher dimension. So I'm going to propose the following conjecture. So the point is the following. So I think that the following is true. So you take the fiber and you complete it by adding 1 point for every boundary component, as we do with punctured surfaces. So when you look at the mapping class group of a surface, sometimes it's more convenient, instead of looking at punctures, to close the surface and to look at the points as marked points. And we do the same here. So F bar is just you add 1 point for every boundary component. Okay, and of course here you get a singular manifold. It's not really a manifold because you get 5 singular points. But it still makes sense to say that this has a singular Euclidean structure. Okay, with a singularity here. The singularity was a bunch of codimension 2 manifolds, and here's the same. So the singularity here is going to be of codimension 2 with codimension 2 singularity. And this codimension 2 singularity is going to be a union of surfaces. Actually, I think it's only one surface. The surface is going to be itself a singular Euclidean structure. No, a Euclidean structure. And there's going to be a cone angle around the surface. In this case, it's going to be 3 pi. Okay, and so moreover, you have two foliations, two orthogonal foliations. It's really exactly like here. Here there was something magic called a quadratic differential that gives you the singular Euclidean structure and the foliations. Here I don't know whether there is some magic object like this, but nevertheless you get both things. You get a singular Euclidean structure and the two orthogonal foliations that are preserved by phi. Okay. The only thing that should be said more with a bit more accuracy is what happens at the boundary. So every point in the boundary is a singular point of this surface. So it's a singular point. But I mean, this makes sense. I think I know how to prove it, but I still have to check many details. So I'm not going to state this as a theorem. But nevertheless, I think that this is the picture that can extend to higher dimension, and in this case, it should be true. Okay. Thank you very much.